Hello, my name is Steve Gollmer. I am a professor at Cedarville University. I've been teaching physics for 27 years. Over the years, my students have expressed appreciation for the fact that as we go through our physics class, there are times where I'll point out how their faith and their science may come in conflict, or at least appear to go in conflict, but that in reality we don't have to somehow turn from our faith because of what we're seeing in science. And so as a result, I want to talk about a selective history of gravity to kind of point out some of the things that I might talk about over the course of multiple lectures. I found that as we do look at the world around us, we have to realize that some of those conflicts are not going to be resolved because of the wonder of God's creation. Others just require us to do a lot more study. So I think as I approach this, two passages from the Bible. First of all, Psalm 40 verse 5 says, "You have multiplied, O Lord my God, your wondrous deeds and your thoughts towards us. None can compare with you. I will proclaim and tell of them, yet they are more than can be told." The more we study the creation, the more we're going to realize there is so much more that we're not going to be able to comprehend because of the vastness of it. When Job was confronted by God, there was a question that was brought to him, and as a result, Job comes up with the following statement: "I know that you can do all things, and that no purpose of yours can be thwarted. Who is this that hides counsel without knowledge?" That's a charge that God made to Job earlier. Job responds, "Therefore I have uttered what I did not understand, things too wonderful for me, which I did not know." So, let's talk about one of those places where I felt that there might be a conflict between my faith and my science. I teach out of a physical science textbook, and the author, Krauskopf and Beiser, has this particular quote: "In fact, few aspects of our knowledge of the natural world are as solidly established as the theory of evolution." It seems to give us the impression that evolutionary theory is so firmly established that it is foolish for us to doubt it. Now, it ends up that evolution has two different aspects, and I'm not going to go into that specifically now, but this idea of a short-term selective selection of the fittest, which I do think can be studied in the laboratory. Bacteria end up by mutating, viruses mutate, and therefore get around our defensive systems. But at the same time, there's a molecules to man type of evolution that does not sit on the same level of confidence as we would on the things that we see in the biological world on the microscopic level. I went to a critical thinking seminar, and the following quote was made by the instructor, and I've since tried to find it in print, but I've never seen it anywhere. But he made the following statement: "Evolution is a better proven theory than that of gravity." Now, we know how gravity works, and to think that evolution is better proven than gravity, I really had to question him. So after a break, or during a break of the session, I went forward and I asked him, I said, "How can you actually make a statement like that?" And he said, "Well, you have to realize gravity is just an observation. Things fall. But evolution is something that has to be proven. Therefore, evolution is a better proven theory than gravity." I challenged him on that because gravity is not just an observation, it also is a theory. And so, as a result, let's talk about gravity. If we go back before the time of Christ, Aristotle, he wrote a kind of a compendium or a summary of the knowledge that was known at that time with regards to physics. Of course, he added a lot to that, but it was taking the current day knowledge and systematizing it in thought. And with that work that Aristotle did, he did say that things have a natural tendency to reach their natural state. So if I have a heavy object, it wants to fall until it reaches its lowest state. Now, if you think back in terms of the Greek worldview, you had four different elements. You had earth, fire, water, and wind. And in Aristotle's thinking is that because earth is more dense or heavier, it will seek the lowest place. The second lowest place that things get sought is water, so therefore water floats above the land. Air floats above the water, and if you have a fire, you notice the fire lofts upward, and therefore fire seeks an upward direction. And so gravity was really more of a description of the things seeking their own. It's just an observation. However, Aristotle also came to the conclusion that the heavier things were, the faster they fell. Now, we know that something weighs more, it's harder for us to hold it in place, and therefore we would anticipate it falling faster. But in reality, it wasn't until the time of Galileo that we have a definitive description of an experiment for determining that all things fall at the same rate. Now, we hear the story of Galileo taking balls and dropping them off the Leaning Tower of Pisa, as illustrated in the PowerPoint here. But some would say that actually is an apocryphal story. But we do know that Galileo did very systematic studies of rolling balls to see what would happen for the distance they would travel if they were on a smooth track, but also if you dropped a ball, would they fall at different rates based on their weight. It ends up that others had actually written about that previous to Galileo, but we attribute it to him. Now, there's a simple experiment you can do. If you just take a piece of paper and you let it drop, it will fall at a certain rate. I don't have enough distance to show it here, but I take that same piece of paper and I crumple it up into a loose ball. Another one where I compact it as tight as I can, and another one where I used a hammer to hammer it as small of a ball as possible. If you take these three objects and drop them, let's say in a stairwell, you'll find that the smaller the ball is, the faster it falls. So there must be something more going on than just the weight of the object, because all three sheets of paper are identical. So it ends up that we can think in terms of something that Newton introduced to us much later in time, that if you add up all the forces, they will, if they're non-zero, they'll add up or will equal the mass of the object times its acceleration. We get this idea of a mass is something different than the weight. It might require me to apply a certain force to hold up the weight of a rock, but the mass of the object consists of how many molecules it's composed of and what kind of molecules. Is it iron? Is it oxygen? Is it carbon? And therefore, it's the combination of the molecules that comprise an object that give it mass, but then there's something that gives it weight. So if we look at the forces acting in an object, as illustrated in the right here, we have the weight pulling downward, expressed with the capital W, but we also have a resistive force of the wind going past the object that's falling. As that wind goes past that object, it exerts an upward force or a resistive force designated by my capital R. It ends up that the sum of those two forces determines what the acceleration of the object is. So if you end up by getting rid of all the air altogether, then all you have is the weight of the object that's causing the acceleration. Well, even from the time of Aristotle, it was known that the weight of an object was proportional to its mass, how big it was and what it was made of, and therefore weight is equal to m times g, and let's just treat g as just some constant. Well, then if we take that top equation, substitute in mg in place of the weight, and assume that we get rid of our air resistance and r is equal to 0, you'll notice that mg equals ma, and if you do a little math, the m's cancel out, and you get the conclusion that g is equal to a. And the acceleration of gravity that we can measure is 9.8 meters per second squared, or, if we're in the English system, 32 feet per second squared. But the question really is g a constant? Now, if we just do a little thought experiment here, if the Earth were flat and the influence of the Earth was somewhat set at the surface, as I move away from the surface, there's no way where that influence can dilute out and become weaker, and therefore I would anticipate that as I move away from the Earth's surface, gravity would stay the same. However, if the Earth is, let's say, a sphere, the weakness, or I should say the influence of the Earth weakens with distance, and therefore I'd anticipate that gravity would get weaker with distance. Well, is there a way of testing that out? It ends up if you take your smartphone and you have a particular app that to be able to measure gravity or acceleration of the smartphone, you could set it down on a table and find out that g is close to 9.8. It'll be slightly off because of the accuracy of your phone. If you were to drive up in the mountains, you might say, well, maybe I can measure the change in g as I go higher in the mountains, and technically that's true. However, the accuracy of your phone is not that good. However, if you had a much more accurate way of measuring gravity, you would indeed find that if you were at the base of a mountain versus the height of the top of a mountain, you would find that g would get weaker with distance, which would be inconsistent with a flat Earth. Now, question is, how do we know that the Earth is spherical? Now, I say spherical in the sense of an approximation. Actually, the Earth is what's called an oblate spheroid. It's kind of a squash sphere. But let's just, for our sake, say it's a sphere. If you go back to the time of Aristotle, it was well established that the Earth was spherical or round. If you looked at the eclipse of a lunar eclipse, you had the shadow of the Earth moving across the face of the moon, and you would find that there is a certain arc shape to that, which would indicate that the Earth is round. Now, some might say, well, that's just the fact that the Earth is a round, flat object as opposed to a spherical object. But if you look at all the different timings that lunar eclipses occur, you still see that same occurrence of a round shape, and therefore we conclude that the Earth is not just round, but a sphere. Probably the most convincing evidence for a spherical Earth is the fact that if you have a ship sailing out to sea, it falls below the horizon. And that would be consistent with a round Earth, not a flat Earth. Finally, the Greeks also knew that as you traveled further north, you found that different constellations appeared. If you moved further south, you saw a different set of constellations, which would also be consistent with a round Earth. So, our best evidence is we just look at Google Earth. You zoom in, you zoom out, you see different locations. That technology wasn't available to the Greeks. But you have to realize that even in the time of the Greeks, it was very well established that the Earth was round. This particular image I have right here is from a GOES satellite. A GOES satellite is a geostationary satellite which orbits the Earth every 24 hours. And since the Earth rotates on its axis every 24 hours, it's always looking down at the same spot of the Earth. So to convince yourself that the Earth really is a sphere, you could look at this GOES image, and it's updated every 10 minutes. You could look at your location on the Earth's surface and see what the weather's like, what the clouds look like, and you'll find out it tracks perfectly well. If this was some kind of fabrication, as some conspiracy theory people would put up, you would have to actually have a higher technology to mimic or artificially generate what you see locally as far as your weather and generate this image as opposed to just setting up a satellite and having it look down and showing us the surface of the Earth. In fact, the experiment that was done by the Greeks was done by Eratosthenes in 200 BC. Notice this is again before the time of Christ. He knew that if you looked at Syene, there is a well there, and on a particular day, the sun shone directly to the bottom of the well. Traveling further north on the exact same day, he found that there was, if you set up a stick lined up with a plumb line, so it was lined up with gravity, it left a shadow on the surface of the Earth on the exact same day. Knowing how far north he was from Syene, he was able to determine then how much of a circle he had traveled, and by looking at the angle of the shadow of the stick on the ground, he was able to infer the diameter of the Earth as well as the circumference, and he came to the conclusion that the circumference of the Earth was 25,000 miles. We find that that's approximately 4% of the current day value. So in the time of Christ, it was well established that the Earth was round. So the question is, why do you have people still feeling that the Earth might be flat? Well, if you go back to the time of Columbus, at least if you look at, if I look back at my history book in high school, actually probably junior high, there was a story related that in the time of Columbus, people were afraid that they're going to fall off the edge of the Earth, that somehow the Earth was flat, and it was a foolish errand of Columbus to actually do that. But the question is, if we are 2,000 years away from the time of Christ, and in the time of Christ we knew the Earth was round, why would this be showing up now? Well, it ends up, there's an author, Jeffrey Russell, wrote a book called Inventing the Flat Earth, and he looks into this flat Earth myth and why it actually appeared in the first place. First of all, there was a statement that there was an opposition to the opposition to Columbus on his voyage was not because the Earth was flat or not, it was actually how big is the Earth? Well, if you look at that picture I have of the Earth on the top there, that is our current arrangement of continents. But if the northern hemisphere and the southern hemisphere, or I should say if the western hemisphere was not there, North America and South America, you'd have something that looks like the following. The people, the religious leaders of the time of Columbus knew that if there was nothing in between Africa, the coast of Africa and the coast of Europe, and he was going to travel all the way over to the East Indies or the Asian continent. That was a long voyage, and nobody would be able to make that large of a voyage. Therefore, to go around the southern portion of Africa was a much wiser trip. However, Columbus adjusted the numbers. He said, well, those Greeks really didn't know what they're talking about, and probably the distance between Africa and, let's say, Japan is really 5 times smaller. He anticipated that his trip would take him about 4 weeks, and even if it took a little bit longer, there probably would be some islands they would find and be able to stop and restock their reserves. Well, it ends up that the story goes that Columbus was fortunate that there really was a continent in between here and there. And as a result, after about 5 weeks or so, he actually did make land, and we had the discovery of the New World. This was not somewhat a triumph of science over religion. It really is the fact that the religious leaders were proven right at the time because they embodied what was currently known scientifically about the world. It was more of an entrepreneur like Columbus looking for a better route and getting lucky. So why is this controversy promoted? It ends up that it's usually used to discredit people of faith with regards to science. If you, as a believer, somehow feel that what science says is wrong, then you're the one that should give in, not the science. And what you have to realize is if we have the world created by God, God's world is going to act consistent with how he made it, and therefore there should not be a conflict between creation and, or I should say, between science and our faith. Danny Faulkner down at Answers in Genesis has done a great job of following up this flat earth issue. In fact, there is a Flat Earth Society out there, and he has some significant concerns with regards to it. In fact, the following quote I'll read here. However, some people promoting a flat earth appear to enjoy watching people squirm uncomfortably when confronted with an argument that they disagree with, but can't quite manage to refute. Of course, these people are not about to let on that they are anything but serious about the flat earth. This is perverse. In fact, people that do participate in the Flat Earth Society, I would say, is there are some that are just lampooning creationists. We're going to make creationists look silly by promoting a flat earth. Another is the fact is there are some people that are taking advantage of others. And finally, there are some that are deceived and feel that it's a test of their faith. How would you feel if somebody said, if you believe in a round earth as opposed to flat earth, you really don't believe the Bible? And Danny Faulkner, in his book Falling Flat, goes through a number of those arguments that are brought up to try convincing people that they have to choose between the Bible and between a Bible and a spherical earth, and show that they really are taking an abuse to God's word. And so we need to be careful that we're using God's word appropriately, as opposed to listening to somebody else. I am reminded of the passage in Acts chapter 17 where it talks about the Bereans. It says the Bereans were more noble because, first of all, they listened to Paul to what he had to say about the resurrection of Christ, but then they went and they searched Scripture to see if this is true. You should never accept things at face value. You should be a student of God's word, so that as you hear some things that may sound like there's a conflict between your faith and science, that you can work through that. So, let's go another little avenue with regards to gravity. With regards to Ptolemy and Copernicus. Now, Ptolemy was a Greek. He, again, just like Aristotle, somewhat accumulated all the current knowledge about astronomy in his time. And essentially, the assumption was that the Earth was at the center of the universe, and that the sun went around the Earth, the moon went around the Earth, and the planets went around the Earth. The evidence for that would be the fact that the Earth doesn't move. It's stationary. And if it were to move, shouldn't the stars shift their position as the year goes by? And since you didn't see any shift of the distant stars, therefore the Earth must be stationary. It wasn't until the time of Copernicus, and notice it was 1400 years between Ptolemy and Copernicus, that Copernicus proposed that it may make more sense to assume that the sun is at the center of the solar system and that the planets and the Earth go around the sun as opposed to the other way around. One thing I do want to point out, if you look at that picture of Ptolemy on the left, notice in his hands he has a little device that's called an armillary sphere. And this painting was done before the voyage of Columbus. And notice here, the art world, the scientific world, the religious world, all knew that the Earth was round, and that armillary sphere is a depiction of the Earth as well as the stars that are around that, which was used for doing astronomy. But Copernicus says, if we make the sun at the center of the solar system, it helps to explain a lot of things. So why didn't people think of this earlier, or why didn't they accept Copernicus' position? Well, it ends up that when you look at planets, sometimes they will appear to move backwards through the sky. And so, in the time of Ptolemy, the assumption was that not only do the planets move around the Earth in circular motion, but they actually move within circles within circles. So think of a spirograph, and I'm not sure if that toy is still used today, but you would have a circle in which you would have a bunch of spokes or gears and little places to put a pen, and as you move it around, you would actually form out little spiral shapes, and depending on where you place the pen and how big of an inner disk you had compared to the outer disk, you could come up with very complicated motions. And to some extent, that's a mental model of what Ptolemy and the Greeks believed, and that worked really well. In fact, they could predict the location of eclipses, the location of the planets with very high accuracy. And therefore, by the time of Copernicus, it ends up that when Copernicus proposed his model, he could not predict the location of the planets with the same degree of accuracy as Ptolemy, and therefore it was not accepted. It wasn't until Galileo comes along to be an advocate. In fact, Galileo has done a lot, and I've alluded to him already with regards to the idea of gravity and things falling. But it ends up that Galileo put a high emphasis on measurement. And as a result, if I had a conclusion about something being right or wrong, my reason is important, but ultimately I have to find out, does this match the reality of the world? And so he used pendulums to give very high accurate measurements of time. He would do things with regards to measuring inertia, which would be related to the mass of an object, as I've mentioned previously, and also balls and friction and all those effects. Well, it ends up that Galileo was able to make himself a telescope. He was not the originator of the telescope, but his first telescope had a magnification of about 8 times. He was able to make several observations, and as time went on, he refined his telescope so he was able to get up to about 20 magnification. We can get something similar by going down to Walmart or some other store and picking up a pair of binoculars that are 20x and see the same thing that Galileo did. But he noticed that there were mountains on the moon. There were sunspots that were on the sun, but they also moved, and therefore he concluded that the sun actually rotated. There were moons going around Jupiter, just like the moon goes around the Earth. And in fact, the 4 largest moons of Jupiter were actually named in the time of Galileo. Also, he noticed that Venus went through phases as it goes around the sun, just like the moon goes through phases as it goes around the Earth. Therefore, Galileo was convinced that indeed Copernicus was right, even though the accuracy of his model did not give good predictions. Well, it ends up in the time of Galileo. Galileo was a bit of a person that didn't leave a sleeping dog's lie, and so he kept writing and poking at this idea and somewhat embarrassed the Pope at the time, and so he was called before the pontiff to recant of his position of supporting Copernicus. It ends up that Galileo does eventually recant, but it's said, and again, whether it's apocryphal or not, that as he left the hall, under his breath he said, "And yet the earth doth move." Galileo believed that the earth indeed did go around the sun. This is another example where people would say, well, here we have Galileo being persecuted by people of faith because of his scientific knowledge. But what you have to really realize is there's a danger in accepting current science and building your doctrine around it. It ends up that by the time you get to Galileo, you had a lot of Greek thinking, Aristotelian science, that was ingrained into the church. And as a result, when scientists tended to find discoveries that contradicted that, it ends up that there was some pushback or opposition. It wasn't that the church was in opposition to Copernicus's view, it was that they had more of a wait-and-see attitude at the time. It ends up that that's probably a good thing for us to do today also, is as we look at modern science, we should not try to adjust our faith to fit the science, but we should hold to our faith as God has revealed himself and look to see how they are complementary to each other, but not to adopt ideas or notions that may be in the future found to be unacceptable or unreasonable. In fact, by the time you get to Kepler, 1619, Kepler makes the following quote: those laws are within the grasp, and especially talking about the laws of the cosmos, those laws are within the grasp of the human mind. God wanted us to recognize them by creating us after his own image so that we could share in his own thoughts. So Kepler, by doing his science, realized that he was actually thinking God's thoughts after him. In the process of looking at the cosmos, the current thinking was that the planets went around the Earth, or if you were in Copernicus, the planets went around the sun in circular motion, and as a result gave poor results. It ends up then, Kepler at one point said, well, what if we did not have perfect circles? What if we had ellipses or squash circles? As soon as he made that concession, he found that the data fit very, very well and it actually superseded the models that Ptolemy put out. The three conclusions that Kepler came to was that, first of all planets move in elliptical orbits with the sun at one of the focal points. If you're going to make an ellipse of your own, take two push pins, put them into a piece of cardboard, put a piece of string between them that's somewhat loose, then take a pen and then pull the string taut and then start inscribing a shape, and you'll find you'll get an ellipse. And the location of one of those push pins corresponds to the focus. The second law that he came up with was that the planets sweep out equal areas in equal time intervals. It ends up that that is commensurate with a principle in physics called conservation of angular momentum. Finally, the third law was that the square of the orbital period is proportional to the cube of the semi-major axis of the orbit. Now that's a lot of words. It's probably easier expressed in terms of formula. P, the period, the time it takes for a planet to go around the sun, if you square that value, it's equal to the semi-major axis. That would be half the distance of the longest distance of my ellipse, designated by the A, if I cube that value. Now, if you've had any science at all, you'll find that that equation doesn't make sense because the units are wrong. On the right-hand side, I have distances of a distance cubed. On the left-hand side, I have time squared. Well, it ends up that in time of Kepler, if you use astronomical units, which would be the distance between the Earth and the sun, and call that 1, and then the time period, or 1 year, the time it takes the Earth to go around the sun, that's also 1. So notice 1 squared is equal to 1 cubed. That matches up. It's interesting that this simple formula, then, if you were to look at the distance that Venus is away from the sun in terms of astronomical units, it will match up with the portion of the year that it takes Venus to go around the Earth. If you want a more accurate representation, you need to look at a constant that is somewhat hidden in that formula, which looks like 1 in this case, but in other units, such as the metric unit, will not be equal to 1. Well, based on the work that Kepler did, we had Newton follow along probably about 70 years later, and he deduced that gravity weakened with distance. Now, I already mentioned before that if you thought of a flat Earth, the gravity should not weaken with distance, but if the Earth is spherical or round in shape, that it should get weaker with distance. Newton built on that idea, and he said that if I were to fire a projectile, we know that it follows a parabolic motion and comes to the Earth. But if I remove the surface of the Earth, could not this projectile actually swing around through the center of the Earth and come back to its original position, which is what we would call an orbit? Therefore, if I fire the projectile fast enough, it will go into a circular orbit, hovering just above the surface of the Earth, if there were no mountains to get in the way, or trees, or other obstacles. And if I fired it even faster, it would go into a larger elliptical orbit. And indeed, this is the basis of all of our space technology, is this orbital mechanics, which hails back to the time of Kepler, but Newton actually relates it to gravity. In fact, gravity is what is called a central force. It's directed between the center of the two objects. So if I have object M1 and object M2, two different masses, there is a gravitational attraction between them. Right now in this room, I am gravitationally attracted not just downward to the Earth, but also to the ceiling. But because the mass of the ceiling is so much smaller than the mass of the Earth, I don't notice that attraction. So the formula I have there shows you that the force of gravity is proportional to mass, but it's also proportional to 1 over the distance squared. So if I doubled my distance from the center of the Earth to my current location, let's say moving out towards space, if I double that distance, the force of gravity gets 4 times smaller, because 1 over 2 squared is 1/4. If I tripled my distance, it would be 1/9 of that. And if you do an experiment, as was done by Cavendish in 1798, Cavendish was able to measure this constant g, and it comes out to be 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Well, let's just do a little connection here. This is for, I'm a physics teacher, so I have to push the physics a little bit further than some of you might want. Let's just do a little algebra here. First of all, I have Newton's second law. The sum of the forces equals mass times acceleration. I've alluded to that earlier when I was talking about gravity acting on an object and the air resistance actually giving you an acceleration different than g. But also, if I have an orbital period and I want to find my velocity, I would just say take my distance divided by time. But the distance in one orbital period is the circumference of a circle, which is 2 pi r, where r is the radius of my circle. Well, from the previous slide, I had the force of gravity as described by Newton, gm1 m2 over r squared. In this case, I'm replacing m1 with capital M. Let's say this is the mass of the Earth. And little m is m2. And then set that equal to mass times acceleration, but I have what's called centripetal acceleration. Now, centripetal acceleration is where I have an object moving in a circle, and as it moves in a circle, notice the radius. If I increase the radius, it's going to end up by requiring a smaller force, or there will be a smaller acceleration if the velocity is the same. However, if I increase the velocity, as the velocity increases, the acceleration increases as the square of the velocity. If I do a little bit of algebra, I'll find that velocity squared is equal to g big M over r. It doesn't matter what the value of little m is. So whether you have the space shuttle in space or the International Space Station or an astronaut, they all accelerate at the exact same rate because their mass cancels out compared to the big mass of capital M for the Earth. And then if we combine both the velocity we receive from the circumference divided by the time period and the relationship we got on the left, we get the following relationship. All I've done is substitute in place for v, 2 pi r over t, capital T, my time period. And then with a little bit of rearrangement, I get t squared equals 4 pi squared r cubed over gm. Notice this is Kepler's third law. In place of t, you'd have your p squared. On the right-hand side, you have r, which is really equivalent to the Kepler formula of a, which is the semi-major axis. Notice I did this for a circle, not an ellipse, but mathematically you could prove it also for an ellipse. And so therefore I have the period squared is equal to some constant times the semi-major axis cubed. And if you go further, you can explain tides with gravity. So as the moon is orbiting the Earth, the gravitational attraction of the moon on the face of the Earth that's closest to the moon will cause the Earth to bulge outward. Now, solid Earth doesn't bulge out as easily as water, so as a result, we see the tides rise. But we also know there's a tide on the backside, and this is due to centripetal acceleration. Now I notice I've put a little bit different representation for centripetal acceleration here. Instead of v squared over r, I have omega squared times r. Omega squared is the angular velocity, or the rate at which the object is orbiting the Earth. And as a result, notice the acceleration of the centripetal acceleration is proportional to the radius. And as a result, on the backside of the Earth, the centripetal acceleration is greater than gravity, and as a result, the water sloshes out away from the Earth, because just as the moon goes around the Earth actually gyrates about the center of mass of the Earth-Moon system. So think of it as you have a bucket of water in the hand and you start spinning, you'll notice that the water wants to slosh out on the outside of the bucket. The same thing's happening on the backside of the Earth. As a result, we have tides not only on the moon side, but on the backside, and therefore tides go through a 12-hour cycle. Well, let's just kind of wrap things up here very quickly, and I don't have time to do that, but gravity has been refined over the years, and it's not until the time of Albert Einstein, early 20th century, that Einstein was trying to resolve some issues with regards to light that we measure and observation. And he came up with both the special theory of relativity in 1905 and the theory of general relativity in 1916. It ends up that special relativity basically says that the speed of light in a vacuum is the same regardless of a person moving or being stationary. Now that ends up by causing some ideas, because if something's moving at a velocity of speed of light to this direction and stationary, if somebody is moving and shining a light, the light travels at the exact same place, speed. Shouldn't the light be traveling faster because of the person that is moving is shining a light? And the answer is no. And as a result, something has to give, and what gives is how we measure time. And this is why people get a little vexed when they think in terms of relativity theory. They say, well, then that means nothing is absolute. In fact, that's a philosophical misuse of the theory of relativity. It doesn't mean that everything is relative and truth is relative. Relativity theory says that everything is relative to the absolute value of the speed of light. So the constant is the speed of light, and as a result, from that constant, we then determine the reality of how things move in space and in time. Well, there were some problems with special relativity, but one thing we did get out of that was E equals mc squared. Now, I'm not going to justify that relationship, but this basically says that the mass of an object, the atoms that it composes of, and how many atoms it composes of, actually are bundled energy. And if you could somehow convert that mass into energy, you would have a significant amount of energy released, because the speed of light is 3 times 10 to the 8th meters per second. And notice we're squaring that. Well, to resolve a number of the issues, Einstein came up with the general theory of relativity. He would say that acceleration results in your clocks moving slower, and that resolved a number of the paradoxes. It ends up that as a result, mass also distorts space and time. So if you end up by sending a signal from a satellite to the Earth, but that signal travels close to the sun, the direction of travel actually bends or changes. Gravity bends light. That's something that's not obvious about gravity, because we think in terms of gravity acting on masses, but light has no mass. So as a result, from Einstein's general theory of relativity, he would actually state that space is distorted. In the time of Newton, when he first proposed his general law of gravity, which was the big G m1 m2 over r squared, the big problem at the time is that people said there is no mechanism as to why things would attract at a distance with nothing connecting between them. According to Einstein's theory, you don't need anything connected between them, because the space itself is distorted, just like you would have, let's say, a bowling ball on a trampoline. It causes it to dent inward, and as a result, the surface of the trampoline is actually distorted or bent. And so if you fire something, it no longer goes in a straight line, it actually bends or curves. That is the mental picture that we have for gravity. What's also interesting is we get this relationship of A is equal to G. Einstein would say that gravity is indistinguishable from acceleration. And this goes clear back to that relationship I gave you earlier, when we recognize that this is called the equivalence principle. and is also one of the keystones of Einstein's theory. Well, some people chafe against Einstein's theory because it just doesn't make sense. It doesn't match with how I think the universe should work. But I'll just give you two pragmatic statements, or I should say examples as to why I'm convinced that relativity theory really works. First of all, E equals mc squared. That large release of energy as you convert mass into energy is what powers nuclear explosions. This particular picture I have here on the right here is of an atomic test on the Bikini Atoll, and you have a large amount of energy released. Radioactivity, a number of discoveries, even quantum physics that were done in the early 20th century, we have found that have been established over and over again through very accurate experiments to have accuracies to 5, 6, 7 decimal places, and therefore relativity theory falls in the same category. Also, probably most of you use GPSs, or geostationary, or I should say global positioning satellites to determine your location on the Earth's surface. It actually consists of a constellation of satellites that are orbiting the Earth, and as you take your phone or a GPS device, it is receiving signals, or very precise timing signals, from several different satellites. It ends up that that timing of those signals have to be very precise, because your device actually triangulates your position based on the timing of the signal received from each of the satellites. If the timing on the satellite is off, then your position is off. And it ends up that because time is affected by gravity as well as motion, it ends up that relativity theory is used to make corrections on your GPS system so that you don't get a false position. Now, if you have a GPS signal, you can get some accuracy, and we usually have accuracy something on the order of several meters, but you can get accuracy to the centimeter mark. If you were to not use corrections due to relativity theory, centimeter resolution from a GPS satellite would be lost in a half second. If you did not correct for relativity theory, you would find that at the end of a day, your GPS would be off by 11 kilometers. It would no longer be useful. As a result, GPS systems help us to see that relativity theory, at least the equations that are associated with it, are accurate and useful. Now, as I conclude here, I really want you to realize is that a molecule's demand evolution does not compare in certainty with our understanding of gravity. The statement that this instructor gave me 20 plus years ago with regards to gravity being, or I should say evolutionary theory being more firm or better proven than that of gravity is just a false statement. First of all, gravity is proven because we have actually expanded on our understanding of gravity, not just being a fallen tendency on Earth, but it's actually a tendency of a force that's exerted out throughout the cosmos. And so we explain the motion of moons and planets and asteroids and satellites, spaceships, galaxies based on this, assuming that the laws of gravity work throughout the cosmos that God created, just as it occurs right here on Earth. It is a theory, it's a well-established theory, and a molecule's demand evolutionary theory doesn't come anywhere close. Second of all, I want you to realize that gravity is a theory that's been proven and improved over millennia. We started with Aristotle, and he had an understanding of gravity. We move on to Galileo, and he added additional details. Newton, even more so, and by the time we get to Einstein, some things that are quite surprising. A lot of people like to think of science as something that's temporary and it's going to change with time. And in fact, that is a true statement. But you also have to realize that the core principles upon which the science is observing is established by God's constant nature, or I should say God's constant creation. As a result, gravity worked just the same back in the time of Aristotle as it does today. So work that Galileo did 500 years ago is also applicable today. What I find in the history, in this short history of gravity, is the fact that it's not necessarily that our understanding of gravity has changed and that somehow Aristotle was completely wrong about gravity. It was that Aristotle's view was incomplete. And so as we study and learn more completely how God's creation works, we shouldn't be surprised that those observations are going to be valid today, 100 years from now, 500 years from now. Also, I want you to realize the complexity of God's creation unfolds as we master basic concepts. The things that Aristotle understood paved the way that Galileo could then add on to, in turn, Newton as well as Einstein. Einstein would not have come up with this theory if it weren't for the yeoman work of all of the scientists that have studied gravity throughout the millennia. And then the final thing, and I guess this really comes down to this picture I have here. This is Matryoshka doll. It's actually dolls within dolls within dolls within dolls. Sometimes people use an analogy of an onion, and science is that way. You understand the outer layer, it might look somewhat simplistic, but once you've mastered that, you can now delve into finer details and uncover even more wonders of God's creation. Not everything will make sense because we are finite and will never understand the full majesty of God's creation, but God wants us to understand His creation, and from that, we're going to gain a greater appreciation for its wonder and majesty and be like Job is, I'm going to come up short, but it's still a beautiful and glorious creation that you've made. If you are interested in studying God's creation in the sciences, in mathematics, in any area of an academic endeavor, I'd invite you to consider Cedarville University as a place to further your education. I have enjoyed my teaching here. I enjoy the quality of students we have, and it's a joy and pleasure to discover God's creation and expand our knowledge of who God is and what He's done.